Hello and welcome to this mini course called Buffer Overflows Made Easy. This is actually a course that was on the YouTube channel or is on the YouTube channel, but has been modified and updated over the years. And I wanted to release this version because it has Python 2 and Python 3 and is a great introduction to stack-based buffer overflows. So we'll go through the buffer overflows in this course, and then at the end, we'll get on TryHackMe and we'll do a walkthrough of a machine that has buffer overflows on it to get a full example of the entire process from beginner level all the way through hacking an actual machine and getting a reverse shell on it. So it should be pretty fun. As always, if you have not subscribed to the channel, please do consider subscribing. It helps us with the YouTube algorithm. It helps keep your content creators motivated and make us put out more and more content for you. So please do consider subscribing, dropping a comment, smashing the like button, all that fancy stuff us YouTubers say. But please, we really do appreciate it when you do hit that subscribe button. So with that being said, we're going to jump right into this with Buffer Overflows Made Easy.
Welcome to the exploit development part of our course. I'm really excited about this because we get to start putting together some of the things we've been learning, including Python and MSF Venom to build our own payloads, and it's going to be really fun. So what we're going to be doing in this course is we're going to be using an attack machine and a victim machine. So the victim machine has to be a Windows machine. So you can run it in a VM. I have a VM here, or you can utilize your own Windows machine if you're running through this course on a Windows-based machine. If you're running on a Mac or you're running on Linux, then you're going to have to virtualize this Windows machine. Now, shouldn't be too big of a deal if you're already running in a VMware situation or a VirtualBox situation. All we have to do is go out to the interwebs here, and if you go to Google and you just type in Windows Evaluation, the first thing that comes up should be Microsoft Evaluation Center. And you just click into there. And we scroll down just a little bit and it says check out the latest products. We're going to say check out Windows. And right here it says Windows 10 Enterprise. That's fine. Now I'm going to be running the whole course through Windows 10 Pro. It really doesn't matter as long as you're on Windows 7 or newer. So if you have Windows 7, 8, or 10, that's absolutely fine. And then you just click through here, say I want the ISO of Enterprise, and then just fill out all of your information, hit continue, get the ISO file and download it, and then load the ISO file into your VMware. That is the option if you are running it virtualized. If you're on a Windows machine, as I will be when I'm running through the course, you do not have to download this part. Now there are two items you will need to download. Both of these are going to be on your Windows machine. So on your victim machine, we're going to have something called Vuln Server. If you go to Google and say Vuln Server is the vulnerable server that we're going to be attacking. So this is a server that we're going to have running on this machine. It's going to allow us to write a custom exploit against this and get a reverse shell. It's going to be really fun. So we're going to actually use the gray corner right here from 2010. If you click on this and scroll down, there is a download button down here. It says vulnserver.zip. Now, Windows may actually block this download. If Windows blocks this download, go ahead and turn off your Defender. I'm going to actually have you turn it off once we start the spiking video, but you can go into Defender and just turn it off in here in Windows Defender settings if you need to. So you have virus and threat protection right here. You can see that I have it turned off. You can just have it turned off. So from here, we can just download our attachment. And I'm just going to hit open because it's a .zip. So again, you're going to need a .zip of some sort. And then I just like to extract this out to my desktop is fine. Just somewhere easy to be able to get to it. And then we can extract the actual or unzip this whole thing right to our desktop. We'll just call this Vuln server like this. Something similar to this is absolutely fine. What's important is that we're able to have all these files on our desktop. So that's exactly what we want here. And then the second part is Immunity Debugger. So if we come over one tab here, We've got Immunity Debugger from Immunity Inc. And this is the link we want to click on. Now what this is going to do is this is going to allow us to run the program through this debugger, and then we can see all sorts of cool stuff. It's a program debugger. So when we are triggering different types of exploits, we can see how it's affecting the memory, the stack, how it's affecting the program, and it'll make a lot more sense once we're in there, but it's really, really nice. So if you scroll down just a little bit, you can see it says download, and it says download Immunity Debugger here. This is all we gotta do, and you can put a fake name in here. You can put Joe Schmo, and then however you'd spell that, and then put a 123 fake street, etc. fake at fake.com, and then fake here, and it should let you download it. You don't have to put in your real information, and see it just works right away. Hit save, and then once it's done downloading, we're gonna go ahead and get this installed. So if it takes you some time for this to download, go ahead and just pause your video, and then we're gonna go ahead and keep going. So I'm gonna say run on this, and say yes. And it's going to say that it needs to install Python 2.7. So we're just going to say yes and say I accept, next, and install. Close that. Now it's going to launch the Python installer. We're just going to do it for all users. If you have an issue with that, you can install it just for you as well. Next, next, next. Let this load, and it's all very, very point and click on this. So our goal here is to be able to write our own exploit code by the end of this, and it's going to actually be really fun. So let's go check and make sure that Immunity ran. And this is what Immunity looks like the first time you load it up. So from here, we've got everything installed. We're going to watch a short video on what a buffer overflow is and how we are going to leverage it. And then we're going to get right into the hands-on portion of attacking this victim machine here from our Kali machine and getting a reverse shell off of this victim machine. So I will catch you over in the next video when we start covering what a buffer overflow actually is. So let's talk about anatomy of memory. So when we talk about anatomy of memory, we have the kernel at the top and we've got text at the bottom. So if you think of your kernel, think of your command line. You can also think about this as a bunch of ones. And your text, you can think about as your read-only code, and you can think about that as a bunch of zeros. So this is only for informational purposes, but we can also call this the kernel the top, the text the bottom. Where we're really going to be focused on, though, is going to be the stack. So if we dive into this memory here and we dive even deeper and we go into the stack, it's kind of similar. So we have these registers here, and I'll provide links down below on how to brush up on some of these registers if you're not familiar. But the important things, what we need to know for this lesson, is that you have the ESP, you have your buffer space, your EBP, and your EIP. So we can think about this again as the ESP sitting at the top and the EBP sitting as the bottom. So what happens is you have this buffer space, and this buffer space fills up with characters. So the buffer space is going to go downward. What should happen is if you're properly sanitizing your buffer space, then if you send a bunch of characters at it, say a bunch of A's, for example, like this, you should reach the EBP but stop. The buffer space should be able to contain the characters that you're sending. Now, however, if you have a buffer overflow attack, then you actually overflow the buffer space you're using and reach over the EBP and into something called the EIP. Now, the EIP is where things get interesting. This is a pointer address or a return address. So what we can do is we can use this address to point to directions that we instruct. Now, these directions are actually going to be malicious code that gives us a reverse shell. So we're going to learn that later on in future videos as we go step by step. So this doesn't have to seem very logical right now. You just have to very, very base level understand that what's happening in the stack is that you're overflowing buffer space. So if you can write over the buffer space and write down all the way to the EIP, you can control the stack and you can control the pointer, and eventually you can have a reverse shell, which will lead to root. So it's going to make a lot more sense when we dive into hands-on. This is just more of a theoretical thing. So let's talk about really quick the steps to conduct a buffer overflow. So the first step we're going to cover is called spiking. So spiking is going to be a method that we use to find a vulnerable part of a program. Once we find the vulnerable part of the program, we're going to do fuzzing, which is kind of similar to spiking. So fuzzing, we're going to send a bunch of characters at a program and see if we can break it. If we do break it, we want to find out at what point we did break it, right? So we want to find something called the offset, and we use that offset to overwrite the EIP, that pointer address that we were talking about. Once we have the EIP controlled, we need to do a few house cleanup things. One is called finding bad characters. The other is called finding the right module. This doesn't need to make sense right now. But once we do that, and we have this information from steps 5 and 6, we can generate shellcode, this malicious shellcode that will allow us to get this reverse shell. So we're going to use that. We're going to point that EIP to our malicious shellcode, and hopefully we're going to gain root. So again, this will all make sense as we dive into the future videos and we get hands-on. So if you look at these videos, these are the videos that are going to come. So our next video is going to be on spiking, second one's going to be on fuzzing, and so on. So if you have trouble with one area in particular, you can watch that area specifically and not have to look through a long video and hopefully break this down into little nuggets. All right, everybody, let's get started with spiking. So before we get started, we're going to do a couple of housekeeping things. First, I want you to disable your Windows Defender real-time protection if you have that enabled. So it looks something like this, where you should turn off this button right here. We're doing that because Vuln Server will actually be blocked by Windows Defender if you try to run it and then run anything malicious against it. So good on Windows Defender for picking this up. This is more recent, as I've taught this in the past. It never used to, but now it does. So we're going to make sure that we turn off this real-time protection. And then we're going to make sure that when we run our programs today, our immunity debugger, and we run our Vuln server, that we're running them as administrator. So let's go ahead and first get our Vuln server running. So remember, I told you to extract that to a folder. Here's my Vuln server folder. I'm going to right click on this and I'm just going to run it as administrator. So now that I've got that running, it should look something like this. And we're also going to run immunity as administrator. So we're going to do that because if we don't, it's actually not going to see Vuln server running as administrator and be able to access it. So we need both running as admin. And the other reason is for Vuln server running as admin is when we get the shell on this, we're actually going to end up as root automatically. So we just want this in the most simple terms. So I'm going to bring immunity over here. And now what we're going to do is we're going to go over here to File, and we're going to say Attach. And if you scroll down, you'll see Vuln server right here. I'm going to go ahead and just hit Attach on that. Okay, in the bottom right corner, you see that it says pause. What we're going to do is just hit Start over here, this play button up top, and now it should say running. So if you're running, then we are good to go. So now we're going to dive into our Kali Linux machine. So I'm in a command prompt in Kali Linux, and the first thing I want to do is connect to Vuln server and see what it is. So by default, Vuln server runs on port 9999, and you need to know the IP address of your Windows machine that it's running on. So once you know that, what we can do is use a tool called netcat. We'll use a switch of NV. We're going to do a connection here, and we're just going to say the IP address. So mine is 1.90, and then the port that you're going to connect on, which is 9999. Okay, so you should see the screen that says welcome to vulnerable server. Type help for help. So it's saying help in all caps. We're going to do that, all caps. And then we get this list of valid commands. So it looks like Vuln server takes commands based on what you enter, right? So there's a stats command, rtime, ltime, etc. So the primary command that we're going to be focusing on is this trun command. Now, when I've taught this in the past, I've left out actually how to find this. So I wanted to teach in depth how we're going to find that trun itself is vulnerable. So we're going to do something called spiking. What spiking does is we're going to take this command one at a time. We'll say like stats, and we're going to say, hey, stats, I'm going to throw a bunch of characters at you and see if I can overflow that buffer that we talked about in the previous video. So do we overflow the buffer? Does the program crash? If it does, then we know, hey, stats is vulnerable. If it doesn't, okay, maybe it's not vulnerable. We'll move on to the next one. So I'm going to show you what a non-vulnerable one looks like and what a vulnerable one looks like, and we're going to look at stats and trun for that purpose. So when we spike, we're going to use a tool called generic TCP, and it's going to look something like this. Let's go ahead and Control C, or actually we'll just type exit out of this if we can. And then what we're going to do is we're going to use, it's called generic send TCP. Let's type that in real quick. Okay, so here is the usage for this. You're going to need the host. Okay, we know the host of 192.168.1.90. You're going to need the port. We know that. You're going to need a spike script. And then you're going to need these skip variables here, which we're just going to leave at 0. So this is what the usage should look like. But we need this spike script. So let's go ahead and talk about that first. So I've already gone ahead and pre-written it. It's very, very simple. So let's take a look at it in gedit. So first we're going to look at stats. So we're going to have stats.spk for spike. So what we're going to do is we're going to read the line. Then we're going to take a string, and the string is stats. Remember, that's what we had here, the stats command. And then we're just going to send a variable at it. Okay, and then when we spike this, we're going to send variables in all different forms and iterations. So it might send 1,000 at a time, then 20,000 at a time, then 5 at a time. It's just looking for something to break the program. So that's what spiking is. We're going to send all kinds of different characters randomly, essentially, to try to break this part of the program. So now we're getting into specifics here. So if you can imagine, we've got the stats.spike. We're also going to have the trun.spike, and the trun is going to have this trun command here. So if you're following along, make sure that you type this out just how I have it, just these 3 simple lines. Go ahead and save it as stats.spike. And what we're going to do is we're going to send this. So again, we're going to say generic send TCP. And then we know the host is 192.168.1.90. The port is 9999. The spike script is stats.spike. And then we're going to just say 0 space 0. Now we've got immunity running right now over here. If you have multiple screens, you can run it on multiple and kind of watch what happens. If we hit enter here, it's going to just be running through this. This is running. You can see that it's taking commands, but nothing's really happening. We'll let it run through all the way just to make sure. And so you're going to see a little bit of a different action when we do have something vulnerable. So we're going through, looks like we're connecting. If we look at Vuln server, you can see that we're actually connecting to the client here and then disconnecting from the client as we send these commands over. So I'm going to go ahead and just kill this for now. You can hit Control C. Doesn't look like it's vulnerable. In a real test, we'd let it run all the way through, but I'm telling you now it's not vulnerable, so we'll just save a little bit of time. So now let's take a look at the trun spiking. Again, should look the same, but you should have a trun.spike similar to this. So if you want to go ahead and type this out, and we have this trun command here. So when we send this spike, I'm just going to tab up twice and change this to trun. And then again, we have to make sure immunity is running. You see it's running in the corner. We're going to go ahead and hit send on this. And immediately immunity starts blinking. What happened? We have paused over here. There's an access violation when executing. Okay, let's go ahead and just kill the process in Kali because we don't need to keep sending all these. So your vuln server has actually crashed. You're not seeing an error message because it's being held up by the immunity debugger. If we were to actually detach or unpause this, then vuln server would crash. So we've hit a violation. This is really good. This says, hey, something's vulnerable here. And if we look at the registers, we can kind of get some information. So one of the informations that we're picking out is, okay, we're seeing this trun command sent, right? And we're sending this trun command with a bunch of A's. So imagine this going into a buffer space, right? Like we talked about before. Okay, we're sending this command, A. In a perfect world, the trun command, or this should all fill into a buffer space, right? All these A's. Well, what's happened here is that it's actually filled over. So if we look at the EBP, remember the base register, right? You see 41414141. That's just hex code for 4 A's. So we've got these here, these 4 bytes, right? And we've gone actually over the ESP as well, a bunch of A's here. Okay, and we've gone over the EIP. So now we've overridden everything. Remember when we talked about in the last video, the EIP is the important factor. If we can control this EIP, we can get malicious and point it to something malicious, right? So that's what we're going to do in the next couple of videos. So I've showed you how trun itself can be spiked and found. In the next video, what we're going to actually be covering is how to fuzz the trun command with a Python script. So that way you can kind of feel out how this process is done in another way called fuzzing. So it's going to be very, very similar where we send a bunch of A's, and it might feel like a little bit of a repeat lesson, but we're going to build out a Python script to do that. And then once we do that, we're going to work on finding this EIP location, because once we control that, again, we can inject malicious code. So step 1 done. I will see you in the next video for fuzzing. All right, everybody. So in this video, we're going to be covering fuzzing. Fuzzing is very similar to spiking in the sense that we're going to be sending a bunch of characters at a specific command and trying to break it. The difference is with spiking, we're trying to do that to multiple commands to try to find what's vulnerable. Now that we know the trun command is vulnerable, we're going to go ahead and attack that command specifically. So a couple housekeeping items. We're going to go ahead and boot up Immunity Debugger again. So we're going to administrator. And we're also going to run vuln server as administrator. So from here on out, you can assume that vuln server is going to be running and immunity is going to be running, and then we're going to have it attached. So let's go ahead and show that process one more time. And anytime that you do crash vuln server, we're going to go ahead and restart it and restart immunity as administrator and reattach. So there are issues sometimes where if you crash vuln server and then you try to reload it with immunity already open, it causes issues. So it's best to just close out of immunity as well, reopen immunity, and start it again. So let's go ahead and make sure everything's running. It is in the corner. Okay, so let's go to our Kali machine now that we have this out of the way. And I've built out a script in Python that we're going to use to fuzz. Let's go ahead and take a look at that script. So we're going to say gedit. I called this one.py. You could do that as well. And if you want to pause the video now and write this out, copy this down, that's fine. You could also do it while I'm talking if you want to save some time. So I'm just going to go line by line and kind of talk about this code, and then we'll see what it does. So from the top, we're just declaring that it's Python. We're going to import a few modules here. We're going to import sys and socket. That way that we can call out the specific IP import. We're also going to import sleep. That way we can sleep it for a second before trying this process over again. So with those imports out of the way, what we're really focused on is we're declaring a buffer variable here, right? So this variable is called buffer, and inside buffer, we have 100A. So we've got this A times 100. So what we're going to do is we're going to say, while true, so we're going to loop this, right? We're going to say, while true, I want you to try something. What we're going to try is we're going to try to connect to this socket. And the socket, all that is this AFI net, that's your IPv4, and the sock stream, that's your port. So we're going to say, hey, let's connect to this IP address. Remember, this is my IP address for my Windows machine that's running vuln server. So we're going to connect to this IP address, we're going to connect to this port, and then once we do that, we're going to send over a trun command. Remember, we spiked the trunk command, found it was vulnerable, and when we spiked it, when we looked at the registers, we actually saw this little bit of extra information here. So we've got this little command that goes after the trun that needs to go in there in order for the program to actually understand it. So that's why this has been added here. So we say, hey, send over this message, send over trun, and then also send over the buffer. So send trun with 100 A's. Okay, then close that connection, go to sleep for a second, and then we're going to append to buffer another 100 A's. So what we're going to keep doing is, as long as there's a connection here, we're going to keep sending you buffers. And it's going to get bigger and bigger. So next time we're going to send 200, then we're going to send 300, 400, etc. until this thing breaks. So what we're trying to do is we're trying to really narrow down where it's breaking and at what specific byte size. So what we're doing here is we're going to fuzz it. And then once it breaks, it should print out an exception that says, okay, fuzzing's crashed at X bytes, right? So let's go ahead and see what that's going to look like. So go ahead and save this file if you haven't already. One other important thing we need to do is we need to change the mode on this to execute. So we'll say change mode +x 1.py. That way we can execute this. And just again to confirm, we've got immunity running. So let's go ahead now and say 1.py. Hit enter. And you should see the connections coming through here on Vuln server. So every time it's doing this, it's sending a new 100 bytes. We can watch immunity for the crash. The crash should happen pretty quick. And then once it does, you can kill the program because sometimes it doesn't kill itself. So it's not the best. There we go. We paused it. No more connections. So let's go ahead, go into Kali, hit Control-C, and we crashed somewhere around 2,700 bytes, give or take. Okay, so let's look at the crash. So again, we see the crash came through, and we've got a bunch of A's sitting here. We didn't look like we actually overwrote the EIP. That's fine. We just need to know approximately where we crashed at. So we'll just call it, for even round numbers, that we crashed somewhere around 3,000 bytes. So what we're going to be doing in the next video is we're actually going to be finding where the EIP is at. So how we're going to do that is we're going to use a tool that's going to create these random, not really random, there's cyclical values that we're going to send out. And then we're going to say, okay, what is the EIP value and where does it correspond in the specific number of bytes that we sent over? So remember, controlling this EIP value, let's go back to it. Controlling this EIP value is what's the most important. Once we can control this EIP value, we do a little bit of housekeeping in our exploit development process, and then we point this guy to our malicious code and we get root. So we want this EIP, we want to control it, and in the next couple of videos, we're going to learn how to do just that. So I will catch you over in the next video when we cover finding the offset. So when we talk about finding the offset, we kind of talked about in the last video, we're going to be looking for where we overwrite the EIP because that's what we want to control. Now, lucky for us, there is a tool already out there that will help us do this. And this tool is provided by Metasploit Framework. It's called Pattern Create. So in our Kali machine, we're going to go ahead and just get that set up. So what we're going to do is we're going to say user share Metasploit Framework tools exploit pattern create. Okay, now we're gonna have to give this a couple switches. Actually, just one for the first one. We're gonna give it a switch of L for length, and the switch of L we're gonna say 3,000. So why 3,000? Well, if you remember the last video, what happened was we found somewhere around 2,700 bytes is where the Vuln server program crashed. And then I said, hey, let's just make it an even 3,000. It'll be nice. This is where it comes into play. So we're going to take 3,000 bytes and we're going to hit enter here. And what's going to happen is it's going to generate this crazy cyclical code here that we're going to actually have to send into Immunity and Vuln server. So you see all this jumbled stuff. All we're going to do is just take it and we're going to copy it. And then we're going to modify our script that we created earlier just a little bit. And I've gone ahead and done that. I'm going to show you what that looks like. So let's go ahead. I called it 2.py. If you want to modify your 1.py and make it easier from the last video, and then I did a little test here just to make sure it worked. But what we're going to do is we're going to paste this value into here. But first I want to cover this script. So remove some things, remove the time because we don't need it. We still have the import sys and socket. We don't need a while loop anymore. We can just say try. And we're going to do the same connection, just try in the connection, make sure we connect to that address. And then we're going to send this offset, right? So I'm going to go ahead and paste that value into here. You can go ahead and work on getting this set up. What we're going to do is we're going to send this value, and then we're going to close the connection. If for some reason we cannot access it, then we'll throw an exception and say error connecting to server, and then we'll exit out. So what we're going to do is when we send this in, we're going to get a value on the EIP. So we're going to see that the program crashes, and then the value on the EIP is going to come back. And then we're going to use a tool, and we're going to say, hey, okay, Metasploit, I found this value on the EIP. What is the offset? So we've got this pattern create right now, and then we're going to have pattern offset here in a second. So let's go ahead and get this saved up. Once you're ready, go ahead, hit save. Same thing again, what we're going to need to do is we're going to need to change the mode like we did last time to execute on 2.py. And also we're going to need to get immunity running and vuln server running. So I'm going to do that really quick here. Okay, it should look like this. Hit play, make sure we're running in the bottom, and then go ahead and fire off that script. Okay, should throw an exception right away. And you see now that we have this trun command that came through with our values that we sent, right? You see the cyclical value goes to the A's. It crosses over the EBP, down the EIP, even comes through the ESP, right? So what we're doing here is we have completely overwritten everything. We've gone too far because we've crossed this ESP, but really what we're interested in is this EIP. We want to be able to control this value. So we see this value in here is 386F4337 right here. This is what we need and are interested in. So let's see how we can make this value of use. So if we come back to this screen, and let's just tab up a couple, and we'll go here and just backspace. What we're going to say is instead of pattern create, all we're going to say is pattern offset. We're going to give it the same switch of L, and we're going to say 3000. But one thing we need to add in here is a switch of Q, and that's for our finding. So our finding was 386 F as in Foxtrot 4337. And now if we hit enter here and we did it right, we should find a pattern offset, meaning that somewhere inside of these 3000 bytes, it found this pattern and it relayed back to it. So if you see here, we actually do have an exact offset match at 2003 bytes. This information is critical because that tells us now that at 2003 bytes, we can control the EIP. And that's exactly what we're going to do in the next video. We're going to look at the EIP and see if we can control it. So we're going to try to overwrite it with very specific bytes and see if those bytes show up. So let's go ahead and move on to there. Okay, so now we're going to try to overwrite the EIP. So in the last video, we discovered that the offset was at 2003 bytes. What that means is there's 2003 bytes right before you get to the EIP, and then the EIP itself is 4 bytes long. So what we're going to try to do is overwrite those 4 specific bytes. So as always, go ahead and get your immunity debugger running with vuln server attached. When you have that, let's go ahead and hop right into Kali Linux. This should be a pretty short video. So what we're going to do is let's go ahead and just gedit the last script that we wrote, which was 2.py. And we're going to modify this together. So what we can do here is we can just delete this offset variable because we don't need that anymore. And instead, we can just write shellcode here. And we'll switch out this offset variable to shellcode. And then let's go ahead and set this equal to A times 2003 plus b times 4. So let's make sense of this real quick. We're replacing what we sent before to find the offset with the shellcode. Now the shellcode's nothing but A's and B's right now, but it's going to get malicious in a minute. So what we're doing here is we're sending 2003 A's. Why? Because that's where the EIP starts. So byte 2004 starts the EIP. So what we're doing is we're sending a bunch of A's, but we want to make sure that we don't overwrite the EIP with A's and have no idea if we're correct or not. So remember, A's are 4 1s, B's is going to then be 4 2. So in theory, we should see 4 2, 4 2, 4 2, 4 2 on the EIP when we overwrite it. So let's go ahead and just fire this guy off. I'm going to save this, and you could save it as .3 if you want. I'm just going to keep it .2 to make it simple. And then what we're going to do is 2.py. Remember, if you did make it a new file, go ahead and change the mode. And since we have Vuln server running and attached to Immunity Debugger, we should just be able to fire this guy off. And it should break the program. So we have pause down here, access violation, great. Okay, so let's talk about what happened here. So you see the EAX, Trun ran through, bunch of A's, we're used to seeing that. EBP, 41414141, good, came through. But look here, the EIP is 42424242. Now we only sent 4 bytes of B's and they all landed on the EIP. Guess what? That means we control this EIP now. So from here, it's pretty smooth sailing. We got a couple of housekeeping things we got to do in terms of finding bad characters and finding the right module to send this to. But once we do that, we're going to generate some shellcode. We're going to point this EIP here instead to that return address that's going to be malicious, and then we're going to gain root. So hopefully this makes sense. Again, just to reiterate, we have controlled the EIP, and now we're going to start to get malicious. So in the next video, we're going to talk about finding bad characters. Okay, so now we're going to talk about finding bad characters. When we talk about finding bad characters, we're talking about this in relation to generating shellcode. When we generate shellcode, we need to know what characters are good for the shellcode and what characters are bad for the shellcode. We can do that by running all the hex characters through our program and seeing if any of them act up. By default, the null byte x00 acts up. So we're going to take a look at what these look like and if any of these bad characters act up in our program. So let's go ahead and actually go out to Internet Explorer or Firefox in Kali. Okay, and in a small update to the course, the link I was going to have you go to, or I did have you go to, no longer exists. So my bad chars now looks a little bit different, but what we're going to do is we're going to go to the first one here, which is the Cytopia. It is actually a bad char generator. It's a tool. You're welcome to download it and set it up. Fairly easy to install with pip if you want. It shows you all the usages, pretty nice and neat. The cool thing, however, is we can just copy what's already here. So this is in your course resources. All I want you to do is right click, copy this, and then we're going to paste this into a script as the video resumes. But this is in your course resources. Check it out. Great little tool. Otherwise, let's go ahead and continue the video. And then what we're going to do is we're going to go ahead and just gedit the last Python script we worked on. For me, that was 2.py. It could be whatever you named your script. And if you recall, we had just overwritten the EIP with 4b. So we're just going to add on to that. So I'm just going to hit enter twice here and then hit paste. And remember we talked about the null byte, this x00 being bad. I'm going to go ahead and just delete that anyways. So we don't even have to run it through our program. So when we're talking about bad characters, what we do here is we run every single character in hex through it, right? So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 0A, 0B, 0C, etc., all the way to XFF down here. So some programs have characters, just let's make something up, for example, say X70. It may be some command that runs in the program that tells it to do something, right? So we don't want to use X70 in our generating of shellcode because then the shellcode is going to break if it uses this X70. So what we do is we parse all of these through the program and we see what looks funny. Basically, it's an eye test. So what we're going to do is we're going to go ahead and save this. Actually, we need to add one more thing. I apologize. We're going to add the bad chars here after the EIP, and then we're going to save this. And then again, if you're creating a new file, make sure you change your mode. Of course, make sure that you have your immunity running and you have Vuln server attached. So what we're going to do now is we're going to fire this off. It should break the program. No big deal. Okay, it comes through. We see again, we've got a bunch of 42s here. But what we're really interested in is the hex dump. So we can look at that dump this way. We could say at the ESP, right click and say follow in dump. Okay, if you look here, let me try to make this bigger. If you want to make it bigger, you can actually go into the text or the appearance, I apologize, and you could say the font to OEM, I believe, is the biggest. Okay, and I will try to pull this up a little bit so it looks bigger here. So what we're going to do then is we're going to look at this hex dump here. And if this is small, I apologize. So what we're doing is we're saying, okay, I sent X01, so we're expecting a 1, 2, 3, 4, 5, 6, 7, 8, 9. Then we expect 0A, 0B, 0C, 0D, 0E, 0F, 10, 11, 12, 13, 14, etc. We go through this whole list, right? Remember, the last thing we sent was FF, so we're looking for FF down here. We go through every single thing and we see if there's anything out of place. Now, heads up, there's nothing out of place here. Vuln server was made to be very easy, very straightforward, so there are no bad characters. But if there were a bad character, it would be out of place. It would not make sense. Like, for example, if you're reading through and you see 10, 11, and then 12 was missing, and then it goes to 13, okay, it's likely that 12 is a bad character. Now, to make more sense of this, I do have bad characters pulled up. Let's take a look at this. So, I've got this dump here instead. So if we look, we've got 01, 02, 03, B0, B0, 06, 07, 08. Okay, so right away, we're missing 4 and 5, right? So we can identify those as bad characters. And what about the rest? So if we keep going through here and we keep looking for these B0s, which is how it's identifying, then we know that those are bad characters. Now, I will say that it's not going to always be B0 that shows up. It's just going to be something that's out of place. And this is definitely an eye test that you're going to have to run through when you do buffer overflows, and you're going to have to make sure you find everything. I have in the past missed one bad character, generated my shellcode, and pulled my hair out for 30 minutes to an hour looking at why it was not working. So if you want to look at this in practice, go ahead. You can pause the video, see if you can identify the rest of the bad characters here. But if not, I'll identify them for you. It's these guys, right? So what you would do is you would write all of these down. You would say, okay, I'm missing 04. I'm missing 05. I'm missing 28 over here. I'm missing 29, missing 44, 45, etc., right? So you want to make sure you notate all of these down, because when we generate shellcode in a couple of videos, you're going to have to remember all of these. But again, lucky for us, the only thing we're going to have to take out when we generate shellcode is that null byte, which we took out here, or else we would see it start with 00. In a second small update to this video, I want to talk about the bad characters here. Now, when I first gave instruction and taught this, my understanding of bad characters was actually incorrect. And as we grow older and learn more, we learn more about some of this stuff. So I'm back with a minor correction here. First of all, the B0 character itself, right here, is okay as a character. Second of all, consecutive bad characters, all you have to worry about is the 4 here. The 5 is actually an okay character. So anytime you have consecutive characters, which we have here, our only bad character is the first character in that sequence, so 44 in this instance. With that being said, I am one that takes caution. I would rather take out 4 and 5 and even B0 and run that and have my shellcode generate. Now, I can understand wanting to understand the technical portion of it and what is right and wrong, and I agree 100%. But your shellcode will still operate if you took out 4 and 5, or if you just took out 4. In some rare exceptions, that might not be the case, but for the most part, and especially in beginner exploit development, that is true. But I did want to add some clarification here. From here, we're going to move on to the next video. Okay, now on to finding the right module. So when we talk about finding the right module, what we're saying is we're looking for a DLL or something similar inside of a program that has no memory protections, meaning no dep, no ASLR, no safe SEH, etc. Now there's a tool out there called Mona Modules that we can use with Immunity Debugger to achieve this. So if you go out to Google and you search Mona Modules, you should be able to find a GitHub page for it. You're going to need to download this mona.py file and put it in this specific folder here. So the specific folder is this PC, program files x86, Immunity Inc., Immunity Debugger, py commands, and you're going to paste it right into here. So go ahead and do that, and then once you're ready, let's go back to Immunity Debugger. And now I already have the program attached, Vuln servers here. And what we're going to do is we're going to actually type in this little bar down here. So what you can type in is exclamation Mona Modules and hit enter. So that'll pop this guy up here. And if you look, what we can see is these protection settings right here. Look, we've got false, 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 false across the board for some of these protection settings. And that's what is ideal for us, right? We've got trues on some of these other things, but really what we're looking for is we're looking for something attached to Vuln server itself, which you can see this Vuln server right here, and we're looking for all falses. So a prime candidate immediately right away is this essfunc.dll. So we're going to go ahead and just keep that in the back of our minds because we actually need to do one other thing. Now, if we know this by memory, we can go ahead and type it out right here, but I want to show you the process for actually finding what we're about to do. What we're about to do is find the opcode equivalent of a jump. So let's go ahead and look at how to do that. To do that, we're going to go into Kali Linux, and we're going to locate something called NASM shell. So we'll just type locate NASM shell, and go ahead and just copy this Ruby right here, and then paste it in like this and hit enter. So when we say we're looking for the opcode equivalent, we're trying to convert assembly language into hex code. So what I'm doing is I'm going to type in this assembly language, this JMP ESP. This is a jump command. So what we're going to do is we're going to use this as a pointer. So the pointer is going to jump to our malicious shellcode, and that'll make more sense here in just a little bit. So the hex code equivalent of JMP ESP is FFE4. Okay, so now what we're going to do is we're going to take this information, this FFE4, and we're going to go back into Immunity. And we're going to type this instead. So let's delete the modules part. We're going to keep Mona. And we're going to say Mona find. We'll do a -s. And we're going to say XFF/XE4. And then we're going to say M for module, and we're going to use this essfunc.dll. So if that makes sense, we've got our opcode equivalent here, the FFE4, and then we've got the module of essfunc.dll, which is right here. Again, we chose this because it goes with the Vuln server program, and it has no memory protections. So this is a good candidate for what we want to do. So let's go ahead and just hit enter on this guy. Okay, and I think I forgot a slash here. Let's check this out. Okay, so that is better. So what we're looking for here is we're looking for these return addresses. So if you look at this 625011AF, that is going to be a return address. So let's go ahead and just write this one down. We're going to go right down the list and find what works. So I always like to start at the top, and you can see here that it found this essfunc.dll, and it's got all the memory protections here listed as false. So now with this information, what we're going to do is we're going to go into Kali. We're going to just type exit here on this NASM shell. and we need to edit our Python script. So whatever Python script you're at, I'm still on 2.py, go ahead and open that guy up. Let's delete out the bad characters because we did already find those. And now what we're going to do is we're going to delete out this B4. So let's write in real quick what our return address was. Remember, it was 625011AF. So now, instead of having 4 B's in place of the EIP, we're going to put this pointer there. So we're going to have the EIP be a jump code, and then the jump code is going to go to malicious code. So we're going to enter that in here. Now we're going to enter it in a little special. So what we're going to do is we're actually going to enter it in like this. We're going to say /XAF/X11/X50/X62. If you notice, this is actually in reverse. So you see AF115062. We're doing this reverse for a special reason. So when we're talking with x86 architecture, we're doing something called little endian format. So x86 architecture actually stores the low order byte at the lowest address and the high order byte at the highest address. So we actually have to put this in reverse order. So what this should do now is this should throw the same error before, but it's going to hit a jump point. So we can do something special in Immunity to actually catch this. Let's go ahead and hit save on this script. And let's open up Immunity again. So let's go ahead and minimize this. And let's maximize this guy again. Okay, so we're going to do something special here. So first what we're going to need to do is we're going to need to click on this little arrow here. It's kind of bluish black. And we're going to enter in this expression to follow, 625011AF. So remember, that's going to be our jump code. So if we hit OK, we should find this FFE4, this JMP ESP, right? And this is perfect. This is exactly what we want right here. So what we're going to do is we're going to hit F2. So F2 will turn it blue. And what we have just done is we've set a breakpoint. So we have the breakpoint running. What this means is we're going to overflow the buffer, but if we hit this specific spot, this jump code, it's not going to jump to further instruction. It's actually going to break the program and pause right here for further instruction from us. And that's all we want. We don't have anywhere to jump to right now, so it's not important. We just need to know that we are hitting this, we're overwriting the EIP in the exact spot we need to, and then we're going to be able to jump forward. So let's go ahead and hit play here. And then what we're going to do is we're going to go back into Kali and we're going to execute our script. So let's go ahead and do that. We'll say 2.py here. Run that. Oh, you know what I did? Apologize here. I never deleted the original code here. So if you caught that, good job. Okay, let's go ahead and try that now. Okay, so we ran it, and what happened? You see breakpoint at ESSFunc.625011AF happened. The program is now paused. We have hit our breakpoint. That means we control this EIP. Look at this, 625011AF. We control the EIP. Now all we have to do is generate some shellcode, point directly to that shellcode, and we are home free with root. So we're going to go ahead and do that in the next video, and I will catch you over there. All right, the video you have been waiting for. This is the last and final video in the course, and now we're going to gain shell. So here's what's going to happen. We're going to use a tool called MSF Venom, and we're going to use that to generate shellcode. So I'm going to go ahead and copy and paste the command over, and then we'll talk about what this command does. So we're running MSF Venom. It's brought to you by Metasploit, and we're going to set a switch of P for payload. So we're going to set the payload for Windows because we're attacking a Windows machine, and we're going to do a shell reverse TCP. So we didn't declare x64 here, so we're going to assume x86, but we'll declare that later just in case. So when we have a reverse shell like this, what we're doing is we're having the victim connect back to us. So we need to provide our information. So by our information, I mean the Kali machine IP address, which is going to be our L host right here. And then we're going to also have a port we're going to be listening on. So that's going to be our L port, our listening port. and we're going to declare that as 4444. I'm setting an exit func equal to thread. All that does is make our exploit a little bit more stable. We have a -F for file type. We're going to export this into C. A -A for architecture, that's x86. And then a -B for bad characters. Here's where finding the bad characters becomes important. So we didn't have any besides the null byte, but it's always good to teach it and explain why it would be important later. So if we had any bad characters, this is where we would put them in. So let's go ahead and just hit enter here. And it'll take just a second to generate this shellcode. And once it does, we're going to copy and paste it into our Python script that we've been using. So we're going to grab this information here. We don't need the semicolon. And it's always good to take note of the payload size. So it's not going to matter too much for us, but if you do go into exploit development, payload size can be everything. It could be that you're working with a very limited space. Say you only have 200 bytes left, and a payload size of 351 is just not going to work because you're going to truncate it at 200. So always good to note the payload size, especially as you dive deeper into other projects, if you do go farther into exploit development. So let's go ahead now and open up our Python script we've been using. So I'm still on 2.py. And I'm going to declare a new variable here up at the top. We're just going to call this overflow. Set it equal to this. I'm going to add a parenthesis, hit enter, and then add a closing parenthesis like that. So what we're also going to do is we're going to come down here and we're going to add in overflow, and then we're going to talk about this. So what we've got here is we've got the shellcode, right? So what's going to happen is we're going to submit the shellcode. In this variable shellcode here, we're going to say, okay, 2003 bytes, that gets us to the EIP. When we get to the EIP, we're going to hit this pointer address, right? This pointer address is just a jump address. So we're going to jump to this set of instructions that we provide. The set of instructions we're providing is this overflow here. So what we need to do before we submit this overflow is actually insert something else. And those are called NOPs. So it's going to look something like this. So it's called X90 like this, and we're just going to add 32 in. And so NOPs are padding, essentially. They stand for no operation. If you've ever heard of something called a NOP sled, that's kind of what it's referring to. So when we have something like this, what we're doing is we're just adding a little bit of pad space in between this jump command and this overflow shellcode, right? So in an instance, if we didn't have this, it's possible that our overflow wouldn't actually work. We wouldn't get command execution on the computer because something interfered here. So we just like to add a little bit of padding in between these two, and that makes it a little bit more safe. Again, if you have a limited space, say we go back to the 200 byte example, you might really need a little bit of padding, like 8 bytes, 16 bytes. You have to play around with it and figure it out. So a lot of exploit development is just messing around with the exploit until something works. So we're going to go ahead and just save this now. Okay, and then on another tab over here, what we're going to do is I'm going to set up netcat to listen. So it's going to be NVLP like this. And then I'm going to put the port to all fours because that's what we declared in our shellcode generation. Okay, lastly, what we need to do is we need to run Vuln server as administrator. We don't have to have it in immunity this time. All we have to do is just make sure it's running. And then we're going to fire off this guy. So we're going to say 2.py, hit enter, check this over here, and look at that, we've got a shell. So now we are on this computer. We could say, who am I? Okay, it's Heath. Heath is me. That's the administrator. Perfect. We are good to go. So we have gone from fuzzing a program, spiking a program, not knowing anything about the program, finding the vulnerable trun command. We used that to fuzz it. We found and controlled the EIP. We found some bad characters. We found the right module, generated some shellcode, and now here we are at root. So hopefully this has been easy for you. My recommendation is to go through and make notes again, try to understand the theory behind what's happening, and also try to understand everything that's going on. This is as basic and simple as overflow can get. Of course, there are memory protections. It's not generally this easy. This is just meant to teach people how buffer overflows work. Hello everyone. So this is a update to the course. It is 2021 and Python 2 is now very much deprecated. So I showed you some tips and tricks and techniques to run Python 2, and it really was all manual method for utilizing Immunity Debugger. And I think the manual method's good so you understand why you're doing what you're doing and how you can go through it. Now I'm going to show you some automated steps that we can use using Mona, and I'm going to show you how to build out our script in Python 3. Now I'm going to semi-speed run through this because you should have most of this already. So I'm going to walk through and talk what is different in Python 3 and what you see and what might look a little bit different. Okay, so the first thing that we're going to do is we're looking at our initial fuzzing script here. And you can see I'm calling out up here user bin Python 3 as opposed to our user bin Python that we initially called. And we're coming through and everything holds true for the most part, except when you come down, we have a couple of differences. So I am putting in a payload of this trun command, right? And we have the buffer that we're sending through. This should look familiar. This is what we did, except we did this in the send command here. All we're doing now is we are encoding this. Now, this might run on its own, although we've seen some issues with Python 3, especially without encoding it, where this will not run. So now we're doing byte encoding, and I'll show you what that looks like here in just a minute when we get to our last script, what it looks like kind of manually and how you can get this to execute. But for here, we're doing byte encoding, and this is allowing this to send. It's a feature of Python 3. We have to declare what we're sending over in the data. So we're sending over these bytes. Okay, so very, very small differences here. The declaration of Python 3 at the top. Everything else holds true, except we're adding this payload command and we're using a .encode to send this over. Other than that, the print command down here, you'll notice prints now have parentheses. Python 3 feature. We don't just do print and then you're used to seeing just the quotes. Python 3 now, you have to utilize the parentheses around a print. So we're doing that. Okay, so simple, straightforward on this script. If you need it, go ahead, pause on any of these and copy it down if you want to try this out. I'm going to move on to the second part here. So when we're trying to find the offset, same exact thing. Notice all I did was delete the buffer. This looks exactly like the second script that we ran in the initial videos, right? But this time, all I'm doing is removing that while loop, bringing this over. This is identical to the script we created. And again, the print command is now in parentheses. There's offsets here and it's just encoded. Nothing different. We generate this the same exact way, and then we find the offset in the same exact way using our tool set. Okay, so we generate this, go in there, see the offset. The offset will be exactly the same. We'll find that it's 2003, and we'll move on to our next script where we try to control the EIP. So again, make sure you're using Python 3 at the top. Just small minor changes here. So now with Python 3 at the top again, our third script, we're going to go ahead and take this, make it into shellcode. This should look no different again. And now we're just going to replace that with the shellcode variable. Same thing. This is even identical. These last two scripts here, purely identical. All we have to do is change offset into shellcode now that we have found that the offset's at 2003. And we're trying to overwrite the EIP with the 4 bytes. So easy breezy. Moving on, this is where we get into a little bit of fun. Okay, so I showed you how to go out and grab bad characters lists, and we did the manual method where we reviewed everything, and gosh, that took a long time. What we can do here is we have the bad characters. Let's just take a look at this script first. Now, this is how we have our bad characters. Again, all we have to do is add the bad characters in, add that to the end of our shellcode, have our shellcode here for the payload command. This is all the same, payload encode, ship it off, we're good. But I want to ship this off, but I want to show you something first. Okay, so let's go ahead and I'm going to switch over to a Windows VM that I have. I'm going to go ahead and load up Vuln Server, and I want to show you a couple commands. So the first command, we're going to use Mona here, and we're going to set a configuration working folder. So what I've done is I've gone in here, and if I went to my C drive and I just created a folder called Mona right here. So go ahead and just create a folder if you want. And what I do now is I declare this is where I want Mona to save data. So I'm just going to say exclamation Mona config, and then we're going to tell it to set a working folder just like this, and then C Mona like this. Okay, you can hit enter on that and it'll say that you have set the working folder. Now, once you have your working folder set, what we're going to do is we're going to go ahead and generate a bad characters list. Remember, we had to go out and find that bad characters list. It's not that difficult, but this is a nice little feature that we can do. So I want to show this to you. We can use a Mona command. So we can just say Mona, and we can come in here and just say byte array, bytearray, and then we type in -cpb, and then we're going to say x00. So what we're doing here is we're generating a payload list for us, and we're saying go ahead and strip out the x00. We don't need that. You could, in theory, just delete this and just run Mona byte array, but here this is fine because it'll take out the 00 for us. We don't need it. You can see that it generated a list right here, but if you go to your Mona folder, it put it into a nice text file here. I'm actually going to delete this and let this all go one more time. So I'm going to let it start off as if we were doing this together. Okay, so this text file here, this byte array, you come in here and look, it's got the byte array generated for you. You can literally just copy and paste this into your shellcode. You don't have to go out and do anything. This will generate it for you. So if you had bad characters you wanted to strip off, say like a 01, 02, it would take that and automatically do that for you. Very nice little feature. It also creates this bin file. Okay, so it knows the characters it's going to be comparing against and looking for. So once we go and we run this, I'm going to go ahead and click the C up here. That's going to bring us back to our normal view. I'm going to go ahead and hit play up here. I'm going to let the program run. And then what I want to do on my side is, and you can run your Python 2 script if you don't have a Python 3 put together yet. But what I'm going to do is I'm going to run this for.py. I'm going to run the bad characters like we would before. So I'm just going to run Python 3 for.py. I'm going to send that off. And hopefully we should have an error over here. We do. We've paused. You can see we got the access violation. We overwrote with the 4.2s. That's pretty common. This right here is where we would right click and we would say follow and dump. And we go manually review everything. Oh, that's terrible. Instead of doing that, why can't we just use Mona? Well, we actually can. So that's exactly what we're going to do. So here we're going to say Mona. I'm going to delete some of this. And we're just going to type in compare, Mona compare. And we give a -f for the file location. And so we're just going to say C Mona. And then we're going to compare this bin file that it generated, byte array.bin. So it generated this byte array bin file right here. It's going to compare that, and it's going to look at the address we give it. So we want to give it the address of the ESP sitting here. So we have in the ESP, we have 010A F9 C8. And this changes. Your ESP value might be different. That's fine. So just enter in whatever you see in your ESP. And I'm going to go ahead here and I'm going to just hit enter on this. And it's going to look for any bad characters. And it says here that the bad character results are 00 and 80. Now, when we manually reviewed this, we didn't see 80 as being a bad character. It says possible bad characters 80. If you see this and you want to generate your shellcode without 00 and without 80, that'd be perfectly fine. You don't have to go through and utilize 80. It will generate shellcode without it, and just to be safe. Okay, but here, I don't say it's false positive. It's just detecting a possible bad character. So you would take this list here and just go ahead and generate your shellcode based on that. So again, fairly straightforward. Now, next step. Remember, we had to find the jump address. We had to find our return address. And we went and we found the XFF, XE4, and we had to do that in more of a convoluted way using Kali Linux. We don't have to do that here. We can actually utilize a Mona command as well to do all this. So I'm just going to make this clean again. And let's actually just go ahead and open up a new immunity debugger, and we'll just go ahead and load and attach Vuln server again so that we have a clean instance. We can let this run. And remember, when we were searching for our ESSfunc.dll. We tried to find the right module when we came in here and we said, hey, Mona modules. And we looked and we saw the ESSfunc.dll and we said, hey, that's good. And we went and found the XFF XE4. Well, we can kind of bypass a step here. Let's say that we identified a module like we did. Now all we have to do is we can just say, hey, I want to find the jump address for ESP. Okay, and then we just say, I want to find that for ESSfunc.dll. And we're going to do that. And we should find a return address when we run that. So it'll bring you to the screen. All you have to do is minimize this. And if you come into here, you'll see that we ran the command. And we have the same results as we did before. So we don't have to go through that whole process of finding the XFF XE4. This will do it for us. And you can see the 625011AF. That is identical to what we had before. So we found the exact same thing. Okay, I'm going to close this out. And I don't think we're going to need this anymore. So I'm going to go back to our Linux and I want to look at the last script that we run. Okay, so this is where things get a tad bit different, and I wanted to show you the manual byte encoding here. Sometimes the payload encode does not work the proper way we want it to. I was running into issues with this, running this script. So the other thing that we can do is manually byte encode this. And so what I've done is I've generated our payload. This is the same thing as running MSF Venom, ran through this, got our reverse shell ready, and I've just put B's in front of every single line. This is telling it we're going to byte encode this. Okay, and come down here, look at the shellcode. There's a B in front of the A, there's a B in front of the return address, there's a B in front of the NOP, or the no operation, and then we've got the overflow, which is already byte encoded here. We're going to send that over, same thing. This time we're going to just say payload, put a B in front of the trun command, and then we're going to send over payload without the encoding, and hopefully everything will work just fine. I'm going to go ahead and execute this script here. So I'm going to open up a new tab, and I'm just going to set a listener on all fours, and then I'm going to just open Vuln server here on its own, and we shall test this and see if it works. So let's go ahead and run Python 3. This is my 5.py. Execute that. Hopefully we have a shell here, and we do. Same process. Again, not much changes throughout this whole thing. I kind of sped ran through this, and it's more or less because I know you already have the foundations down. Now it's just changing this to the modern times and changing this to show you some of the easier tips and tricks. So when you're looking through these, just go ahead and note Python 3, note the subtle differences of having to encode and having to have a separate variable down here. And then the subtle differences of using parentheses for your print commands as well. Everything else, for the most part, stays the same. There are differences between Python 3 and Python 2 that are more significant than this, but in terms of our scripting and what we have to do, not very significant for this aspect. So again, note the payload encoding. If you're running into any issues with Python 3, putting a B in front of your payload is a good practice, good idea. So all right, that is it for this video. I will catch you over in the next section.
Okay, let's put all the concepts that we have learned into practice. Now, what we're going to do is we're going to use a website called TryHackMe. You can go to tryhackme.com. This is a paid subscription required room to do. So what we're going to have to do is, if you have a TryHackMe subscription, you can absolutely follow along. If you do not have a TryHackMe subscription and you want to follow along, I highly, highly recommend getting a 1-month subscription. I'm not paid to say that. I just think it's a great platform. And with that, if you do not have the funds or you don't want to subscribe, you're indifferent, just sit back and watch the video, understand the process, see it done one more time, and that will help you understand the buffer overflow process from start to finish in one full swoop. So with that being said, we're going to go ahead and get right into the box. We're going to be doing a room called Brainstorm.
So I was perusing the old TryHackMe the other day, And on my dashboard showed up this box. It's called Brainstorm, and it's featured, but it really doesn't have a lot of upvotes or a lot of users. Difficulty was medium, and it said, hey, reverse engineering. It's like, I don't really do a lot of reverse engineering, especially on stream or on videos, etc. So I dug into the box, ended up finishing it, and I thought it was really great. It felt like the old school OSCP or that PTP type exam where you have to go in, you have to do this buffer overflow in order to pop a shell and get root, right? So I kind of want to show that off. So what we're going to do is I'm going to come in here and I'm going to deploy it, which I've already done. And I am actually actively scanning the machine. Now we did this box on stream and the Nmap scan lasted the entire stream when it was like 7%, 10% done. So there is no ICMP to this, so I'm just scanning all ports with the PN value here. And as I say that, it shows up. So we have some ports open. We've got port 21, 3389, and then this 9999 Abyss. Okay, so what I want to do is I want to go over to FTP and just check out what's going on. And I go to 1010, 131, 179. We log in anonymously. And if we ls in here, you can see that there is a chat server running. So that's what I'm curious about. What is this chat server directory? Let's go ahead and cd into chat server. And let's see, cd chat server. I don't know why I pulled exe, maybe because it's in the same folder I'm in. All right, and then you can see that there's a chat server exe and an essfunc.dll. All right, so what I want to do is grab these. This looks like an executable. Since this is going to be a reversing and a exploitation, we're going to need to grab the exe and the essfunc.dll to actually extract it and try to exploit it locally before we try to target this machine. So I'm going to go ahead and just do a prompt off. That's not going to prompt me when I go ahead and grab this. I'm going to switch to binary instead of ASCII. Binary just has a little bit better of a transfer, and I've noticed with ASCII when I transfer files over, sometimes they get corrupted. I never had the issue with binary. So I set it to binary, and then all I'm going to do is just say mget asterisk. Now, since this is an executable, I'm going to use Windows in order to reverse this or in order to exploit this. So let's go ahead and say bye here. All I've done from this point, all I have done is spun up a Windows 7 machine. You can use Windows 7, Windows 10, whatever you want. Windows 7, Defender is off, firewall is off. This has no protections on this server whatsoever, or this machine whatsoever. I have the chat server here. I'm going to run this as an administrator. I just want to see the basic functionality of this chat server. And here you can see it says chat server started, called essential function DLL, which is the essfunc.dll, and it's waiting for a connection. So I'm going to go ahead and make that connection. I want to see what happens. Let me pull down the IP address of this machine. And the IP address of this machine is 192.168.449. So I'm going to go grab that and switch over here. So I'm just going to netcat to 192.168.449 on port all nines because that's what showed up in our Nmap scan. If we scroll up, the Abyss is where I'm guessing that the server is because it's not 21. 3389 is RDP. So let's go ahead and take a connection guess at 9999. And here you can see Brainstorm Chat Beta has shown up. Now it says, hey, please enter your username, max 20 characters. And when it says max 20 characters, my wheels start spinning. Well, hey, maybe we have a buffer overflow opportunity here since it's only letting us do 20 characters. Maybe we can do 21 or 1,000 or whatever we want here to see if we can overflow this and crash the program. So I'm going to generate a ridiculously large size amount of A's. I'm just going to create a new tab. And I'm just going to say something along the lines of Python command. And the command I'm going to give is just going to be print A times 5,000. So I'm going to generate 5,000 A's here. And I'm just going to copy and paste that in. I'm just curious to see what happens. We're just fuzzing the program right now. Okay. So I'm going to fuzz it with this. Go ahead and hit enter. And let's go over and see what happened. And you can see that a bunch of A's came through, but not 5,000. Looks like it might be 20-ish or close to it. So maybe it is correctly handling the buffer space there, or the amount of characters we're sending. Now, we also have to send a message. Okay, so we could just say hello and see what happens here. You can see, hey, A said hello. What if we send a really long message though? And we hit enter. Well, now the program freezes up. And if we go check it out over here, you can see that the program also froze. So this isn't great for the program. It's great for us, not great for the program. So this is telling us that the program has crashed. What I want to do is I want to use a tool called Immunity Debugger. And I'm going to do my best when I record this video, and in post, I'm going to come in here and zoom in on different locations of the screen that I think are relevant. Though the font is going to be sort of small if you're watching it from a full screen perspective. So I'll do my best in post here. But I'm going to go in here and I'm going to open the file. And you could just come to open and say, hey, chat server's on the desktop. I'm just going to say chat server. Open that. And it's going to load this program here for us. So now I'm going to hit play a couple times. And the program is running. The program's running here. Everything's going the same. You can see we've got the registers over here. And again, if you have no idea what I'm talking about, please, please, please watch the Introduction to Buffer Overflows series. Say that 3 times fast. Introduction to Buffer Overflows series, or Buffer Overflows Made Easy. Will make a lot more sense of this, okay? So you come into here, and we have this situation where we are sitting here with the registers, we're running, we just need to send over this again and see what happens. So I'm just going to say, okay, my username's Heath, and I'm just going to paste all these A's and see what happens in the program. So what happens is down in the bottom corner, it says that it's paused. That means we did something to break the program. And if you come into here and you look at the EAX, you look at the ESP, you look at the EVP and the EIP, okay, you see all A's everywhere. The EVP is 41s, EIP is 41s, and 41 is hex code for A. So A. Okay, that's good. So we sent a bunch of A's, we've overwritten the EIP. The EIP is our pointer, which we're going to use to point to something malicious. We got a long way to get there, but we can overwrite the EIP, and that is important. If we can overwrite the EIP and we can control the EIP, we can use that to point to something malicious. That's exactly what we're going to do. So let's go ahead and figure that out. How do we find out where the EIP is? We've sent over 5,000 A's, right? And we've only got these 4 here that we need to figure out where they're at. Well, we can use the little tool that's built into Kali. Let's go ahead and just hit Control-C here. And that tool is called MSF Pattern Create. And we can just give it a length, and we'll say, hey, let's give it a length of 5,000. That's the amount of A's we generated. Let's generate the same length here. While it's generating, I'm going to go back to Windows, and I'm going to close out of this. I'm just going to reopen this as an administrator. And I'm going to reattach the Immunity Debugger, or the chat server, sorry. And I'm going to run it again. So I'm just make sure everything's running. I'm going to come into here, and now you can see what's generated is this cyclical value. You can see it goes AA0, AA1, all the way through. So what I'm going to do is just copy this, and instead of sending a bunch of A's, I'm just going to send this over and see what happens. So I'm going to connect back. I'm going to enter a username, doesn't really matter, and then I'm going to paste in this value. Hit enter. This will also break the program. It's the same thing as sending 5,000 A's. The only difference is you can see the pattern comes through. Look, it starts up here, a bunch of A's, and then it goes down to the ESP. You see CP2, CP3, etc. going through. But we also overwrite the EIP with this value of 31704330. That's what we need to note, 31704330. So what we can do is we can come into here, Control-C, and we can say MSF pattern offset. We could say, hey, we gave it a length of 5,000, and now I want you to find out of all this cyclical value that we just sent over, where the heck did that EIP start? So we're going to do that with a Q, and I've already forgotten the hex here, 31704330. So 31704330. Go ahead and hit enter. Cross your fingers and hope that it finds an offset. If it finds an exact match, we're good to go. So it did find an exact match. It says, hey, we found an exact match, and that exact match is at 2012. That means if we send 2012 A's, the 2013th item that we send, or byte that we send, will be the first beginning of the EIP. Now you see that the EIP is 4 bytes long. We need to send over 4 bytes. And we can do this with a quick test by sending over 4 Bs instead of sending over a bunch of As, because we won't know if we just send all As. But if we send 4 Bs and we can control the EIP with those 4 Bs, then we know we're good to go. We can keep moving forward. And that's exactly what I want to do. So let's go ahead and do that. I'm going to make a directory. And we'll just call this buffer overflow, because that's what we're doing. I'm going to cd into buffer overflow. And I'm going to gedit here. We're going to call this overflow.py. All right. And I will zoom in on this as well as I can. So here we go. We're going to import socket. We're going to import sys. And we're doing that because we're going to use socket to make the connection out, right? We're going to have to connect to, just like we're doing with netcat, we're going to have to connect to the open port and IP. We're going to import sys, and we're going to go ahead and define a couple things. We need a username. When we first send over the chat to chatbot, it says, hey, what's our username? And we always say Heath. Well, I say Heath. You could put in whatever username you want. The only thing over here is I'm going to put a B in front of this, so we send this as bytes and not a string. And for the message, what we're going to say is, I want to send over 2012 A's. And then I want to send over 4 B's. Remember, we want to see if we can overwrite the EIP. So I'm going to send over those 4 B's. And now we actually need to make that happen. So we're going to write a try statement. We're going to say, hey, try to do this for us, will you? And we're going to just say print sending payload. Okay. Next, we're going to just define our variable of s. This is very standard. We're just going to say our socket.socket, our socket.af inet, and socket, if I could type, dot sock stream. And this is just saying, hey, let's set this very, very long thing equal to s. And here, this is AF inet is your IPv4. Sock stream is your port. So now we can just say something like s.connect and then say, I want to connect out to 192.168.449. And I want a port of 9999 because that's where it's at. And then once that connects, we're going to receive. And I'm just going to receive some data back. I'm actually going to do that twice just to be safe. I didn't test this with one. It could easily just work with one, but I always receive twice here just to be safe. And then what I'm going to do is I'm going to send over that username. So I'm going to say, hey, username, which is Heath up here at the top. And then I'm also going to need to hit enter on that. So I'm going to make this into bytes as well. And I'm just going to say return new line, right? Return carriage, new line. And that'll be like we're hitting enter on that. We're going to receive the data that comes back because remember it asks us then, it says, hey, what message do you want to send now that you've given your username? And we're going to go ahead and send over that message. That message is going to just be very similar. Message here being the 2012 and the 4 bytes, or 4 B's, I should say. And we're going to come in here and we're just going to go B, RN, just like we did before. We're going to receive one more time, though we're going to crash the program. I don't think this actually receives, but you never know. And then we're going to close the connection out. If for some reason that doesn't work, we're going to throw an exception. That exception is going to say, hey, cannot connect to the server. Just like that. And then we're going to do a sys exit. Okay, so pretty straightforward. All we're doing here is we're making a connection to the port. We're establishing a variable, making a connection to the port and the IP address, receiving whatever message it sends to us. We're going to go ahead and send over a username, which is right here. We're going to send over our message, which is right here and is malicious. And then we're going to receive any other data that comes back and close it out. So let's go ahead and save that. I'm going to, well, it looks like I'm going to open a new line. We'll just keep this open. And let's clear this out. And we'll make that connection again. Let's make sure that this is running a new instance of Immunity. So I'm going to come in Immunity. I'm going to attach that chat server again, hit play a couple times. And what I'm looking for is the EIP to overwrite with 4 B's. So let's go ahead and send this over. We're just going to say netcat 192.168.449.9999. Actually, we're not going to do that. I'm stupid. We're going to say Python. We're going to cd into buffer overflow. And then we're going to say Python 3 overflow. Why do we just write the whole script in order to netcat? We don't need to do that. I have invalid syntax in my line 11 because I am silly and forgot this. All right, let's save this real quick. Try running it one more time. Noob City over here, guys. Noob City. Okay, so we say paused. Right here, you see it paused, and then if we look at this closely, you see that the EIP is overwritten with 42424242. Perfect, beautiful. That's what we want. We control the EIP. Now, from this point, we need to do a few things. We need to find bad characters. We need to find the right module. This is all from the lesson that you should have seen by now, or your basic understanding. And then we're going to use malicious shellcode and get there. So let's go ahead and find bad characters really quick. I'm going to close out of this one more time, reopen immunity, and I'm just going to hit play once I open the chat server. And what I like to do is I just like to come out to Google and I'm going to say, hey, Google, show me bad cars or bad chars. And there's a scripts right here. Usually I go to Bulb Security, which is Georgia Weidman's site, but it's kind of slow sometimes. So I'll just copy this bad chars variable right here. And I'm going to come into here and paste it. Now, I'm going to add this bad chars in right down here to our message send. And I got to give this all bytes. So bear with me for a second. If there's an easier way to do this, please let me know, because otherwise I just noob out when I do this. And save that real quick. Okay, so this is going to send over bad characters. Remember, the X00 is a bad character by default. It causes a lot of issues, and we just leave it out because even if we send this over right now, it's going to cause issues. We just want to make sure we send 1, 2, 3, 4, 5, 6, 7, 8, 9 all the way down to FF. And we're going to save this. And what's going to happen now is when we send this over, hopefully, we catch it. We have an error over here. The program is paused. And what I'm going to do is I'm going to right click on this ESP. And I'm going to say, hey, follow and dump. Now, if we zoom in over here on this dump side, you can see we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 0A, 0B. Okay, there are multiple ways to do this. This is kind of the long way, and it's absolutely fine. What you want to do is you want to look through this and see if there are any blurred characters, any missing characters, anything from your list, what you sent out. So you have your list over here. That's the 1, 2, 3, 4. You want to do the same thing. You want to come into here and just make sure that all the numbers and letters and everything else match. Here they do. The only bad character we have here is the 00 itself. Okay, so the X00, that's it. So I'm going to go ahead and close this one more time. And what we're going to need to do now is we're going to need to come in here and we're going to need to find any sort of protection modules that might exist or protections that might exist on this. So I'm going to attach and run this again. I'm going to use Mona. Now you should know what Mona is. We're going to do Mona modules. And Mona's just going to come out and search for this information for us. So I'm looking. And it's going to come in here and it's going to say, hey, are there any sort of protections like ASLR or Safe SEH or DEP or anything along those lines that might give us some sort of issue? And what we're looking for is falses across the board. False, 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 false. Well, 2 of those show up. We got the executable itself and we got the DLL. If we only had the executable, we would target the executable. But in this case, we have a DLL available to us. Let's target the DLL itself. So we know the ESSfunc.dll is probably the module that we want to target. With that being said, we can also do another search, which is a find. And we can come in here, we can say Mona find XFF/XE4. Now this is a JMP ESP. So this is a jump. We're going to use this to find a return address that's going to jump and allow us to point to malicious shellcode. So we need to find that return address that it contains this XFF/XE4. And I'll show you what that looks like. So once we do that, we're going to say, hey, find that in this module, this ESSfunc.dll. Please find that for us. It's going to do that. It's going to search, and it's going to find a few of them. We can copy any one of these. I like to start with the first one and move down. So you see 625014DF. 625014DF. And I'm just going to delete the bad characters here. And I'm going to write in 625014DF. And we're going to have a variable here called payload at some point. So I'm just going to type in payload is equal to, I'll put this in quotations even though we're going to delete it. Now what we want here is we want this 625014DF to become the overwritten 4B. So we want this to be the EIP. When we hit the pointer, we want the pointer to hit the jump. The jump is going to jump then to our malicious shellcode. So here's what we're going to do. We're going to take this and we're going to write this backwards. We're going to say XDF, X14, X50, X62. Just like that. Okay, and then I'm going to close out this payload. We're not going to put anything here right now. But what's happening here is we want to make sure that we can hit this. So we want to make sure that we actually hit this as our EIP. And what we're going to do is we're going to come into here. I'm just going to click on the C because I haven't run anything yet. So the C up top will do this. So this is running. All I want to do is come up here and hit the blackish, bluish type arrow. And then we're going to search for that 625014DF. Go ahead, type that in and search. Hit OK. And you can see that it says JMP ESP. That's exactly what we want. And JMP ESP translates to FFE4. Remember, we searched FFE4. When I said we're searching for JMP ESP, that's all we're doing here. So I'm going to go ahead and hit F2 on this. And F2 will light this up blue. That says I'm setting a breakpoint. All we want to do is set a breakpoint at this time because we're going to run this script and see if it triggers that breakpoint. And now it says cannot connect to server, probably because I left something bad in there. Yep, let's delete this and then let's go ahead and save and try one more time. Okay. And you can see down here at the very bottom, it says breakpoint at ESSfunc.625014DF is triggered. Okay, we've paused the program. Again, we've triggered right where we want to be. We hit that breakpoint. That's fantastic. Now what we want to do is we want to write a malicious shellcode, write out malicious shellcode so that we trigger a reverse shell in this machine. So all I'm going to do is I'm going to run chat server as admin and hit yes. I'm going to come in here and I'm going to now generate some malicious shellcode. And I'm just going to say something along the lines of MSF Venom. We're going to do a payload of Windows shell reverse TCP. Why are we doing that? Because the program we're attacking is x86 architecture, not x64. We're going to write an x86 payload for this. We're going to set our L host equal to 192.168.451. We're going to set our L port. I'm going to do all 7s. And then I'm just going to set a bad character of x00. Remember, bad characters are important, but here all we have is 1. So if we had another one, say 01, we would just do x01 here and so forth, but we only have the 00. I'm going to do a file type of C. Now, file type is important. Somebody asked on stream, are we generating this in C for any reason? Yes, maybe. The different types of encoding that you use and the different types of file type that you select will generate shellcode that will be different file bytes or size bytes. Okay, so the payload size is 351 bytes. If we generate this in something else, say something like Python, which we can, that'll generate maybe a different payload size. The different encoding will generate a different payload size. So you just got to be careful that you don't run out of room. Now, we're not going to run out of room in this instance. It's just something to note. And what I mean by run out of room is we sent over 5,000 bytes, but maybe we only had 3,000 wiggle room here or something along the lines. And so far, we've sent over 2012 plus 4 bytes, so we got 2016. Maybe if we send over this 300, we're fine, but maybe if we had 2,500, we might not be fine. We might have to look for a smaller payload, just as an example. So here, what I'm going to do is I'm going to go ahead and actually just paste this like this. And I'm going to noob out again and just put B's in front of everything really, really fast. And then we're going to send this over and see if we can't pop shell. So what I'm going to do is I'm going to set up a listener at my IP address and also drop in this payload right here into the send. Now there's one other thing that I want to do. I'm going to throw in some NOPs here, no operations. I just want to add a little bit of padding between the server, or between this JMP ESP, this return address, and this payload. So let's go ahead and add that in. I'm just going to say B here, and we're going to do X90, and we're going to do 32. You could pick a number and see if it works, and if it doesn't work, try something else. But I always do 32 to start. We can minimize it, make it bigger, however we need to do. So what's going to happen is it's going to send the message. It's going to hit the JMP ESP. We're going to send a little bit of padding, just no operation, nothing going on, a little bit of padding. Then we're going to come in here and we're going to send the payload, which should pop shell back to us. So let's go ahead and save this. I'm going to come in here and I'm going to listen on netcat on all 7s. Now I'm going to push this payload off. Let's clear screen real quick. Send that, cross your fingers, and look, we've got a shell. Who am I? You can see I am TCM on this computer. Net user TCM. You'll see TCM's actually part of the administrators. So we've owned an admin account running this service that is faulty. Now, our goal is to own the machine on the site itself. So the IP address that we are attacking, let's go back, is 10.10.131.179. So let's go ahead and modify this script. And we're going to say, instead of attacking us, go ahead and attack this. And we're still going to listen back, but we still have to modify a little bit more. Let's kill this. We'll set up a new listener. We'll come here, and we're going to generate a new payload. Now, the payload I'm going to do, I got to grab my IP. I think I know what it is, but I'm going to make sure. 10.11.4.114. So I'm going to come in here and just say, okay, my L host instead is 10.11.4.114. L ports all 7s. The rest looks good. I'm fine with that. And this is the basics behind doing reverse engineering. A lot of you got confused with the actual buffer overflow lesson in terms of how do I get on the victim machine to run this? And the answer is you don't. Typically, you'll have an application, and this is true with any exploit development. You have an application, you come in here, you fuzz it, you make sure you write the exploit the way it needs to be, and then you execute it against the target that is running a malicious service. And that's exactly what we're going to do. So we'll come in here. I'm going to change this out. Just paste this. I'm going to noob out one more time and add a bunch of Bs. And if we are lucky, we are going to connect to the server that we're sending this over to. I do believe this is a one and done type deal. So we're going to keep our fingers crossed. If we overwrite the server and we do not connect back, then we are maybe going to have to reset the machine. So let's keep our fingers crossed. We've got a port listening. Let's go ahead and try sending this over. And we triggered. So who am I? And we are authority system on this machine that we popped. So that's it. We popped the machine. Now we can go grab our flag, do whatever we need to, answer this out, the rest of the questions that it wants us to answer, and we're good to go. So hopefully that was informative for you. I like this kind of stuff. This is a little bit different than what we usually do. We usually just do walkthroughs, but I kind of want to do some reverse engineering. And if you could do this machine on your own, you will be fine on any certification exam unless your certification exam is like heavy reverse engineering. So with that being said, that's it. If you enjoyed the video, of course, please do hit that like, subscribe, and check out my other videos on my channel if you do have some time. So until next time, my name is TCM, and I do thank you for joining me.